Hi everyone, my name is Newman Waters. I'm one of your head PIs for this semester, and I'd like to go over how to design a counter. More specifically, I want to teach you how to design an arbitrary counter which goes in any order, can go upwards, downwards, really can count in any sequence like 1, 9, 6, 5, etc. So I'll just give a sequence here that we can work from and start designing. So I want my counter to go in this order. I want it to start at 1. I want it to go up to 3. I want it to then go up to 4, 5, and then I want it to skip 6. I want it to go 7, and then 1. Alright, and I'm just doing this to showcase that you can design this however you want. And if you want it to just go 1 through 9, you can also do that. And we're going to be working with a 3-bit counter. 3 bits meaning that you can only fit up to 7 numbers in the or 8 numbers in the sequence. So we've got 1 to 3. So we got 1, 3, 4, 5, and 7. So that's 5 different numbers in the sequence. Obviously 1 repeats here, and we can visualize this a bit better by drawing it out like this. So it starts at 1, goes to 3, goes to 4, goes to 5, goes to 7, and goes back to 1. So you see it's a closed loop, and there are also some numbers that you will not see at all in the sequence. So how are we going to actually interpret this counter? This counter circuit that I've drawn here has these 3 signals, Q2, Q1, Q0. We're going to interpret this as a binary number, so I'll just write it as num, and then it's going to be Q2, Q1, Q0. Alright, so whatever we read out, Q2, Q1, Q0 is the number in the sequence. So if it's 5, these outputs should be 0, 1, or 1, 0, 1. Alright, etc. And that's how we're going to interpret our counter. We need to have some combinational logic, which you can see in this block here, that dictates, okay, what is the next value that needs to be sent out to these outputs here? Right, and this might be a little weird, but what we have to do is we have to feed in whatever we have right now, okay? Whatever our output is right now, feed it back in as an input to our circuit, and then what we do is we design combinational logic as if Q2, Q1, and Q0 are inputs, and then the outputs here of the combinational logic, which we can designate as something like Q2 plus, Q1 plus, and Q0 plus, those are going to be our outputs, and so that's what it'll look like in any truth table that we design. So what we can do is we can write out the truth table for this as if Q2, Q1, and Q0 are inputs, okay? And then Q2 plus, Q1 plus, and Q0 plus are our next state outputs. So this is next state. Oops. And this is current. And you'll kind of see what I mean once I start filling this out. So let's put in all of the possible combinations of Q2, Q1, Q0. And we'll do this in counting order to make it simple. So this is all 8 combinations of the inputs that we could have. However, if you look at the sequence, we don't actually use some of these things, because remember, these are our Q2 to Q0 values. But when, in this first case where it's 0, I'll just write them out so it's easy to, oops. When, our number is 0, well, what's going on? We don't even have that in our sequence. So what this means is if we have Q2, Q1, Q0 all being 0, we don't even care what the next state is. It's never going to happen in our circuit, so we're just going to ignore those things. Now, if our inputs are 1, so if our current state is 1, we're in this state, what do we want our next state to look like? Well, we want it to be 3, right? So what is 3 in binary? We just filled it out. So we do 0, 1, 1. And that, models this transition here. Now, if it's 2, we don't have a 2 in our sequence, so this is never going to happen. It's never going to occur inside of our counter, so we don't care about those outputs there. They have no impact. 3, well, 3 goes to 4 in our little circle there, so that means that we write 4. And then 4 goes to 5, so in our table we say 4 goes to 5. And then 5 goes to 7, right? Just based on the table, based on the diagram there. And then 7 goes to 1, or 6 goes to nothing, right? Because we don't have anything. And then 7 goes to 1. And so this is our truth table for our current state, next state. It's relatively easy to understand. It's just a direct mapping of this that we've got here. Now the important thing to note is that we are using D flip-flops. So we've got these 1, 2, 3 D flip-flops. They have specific behavior. They're relatively easy to understand. Essentially whatever goes in is whatever comes out after a clock cycle, so you don't really have to deal with any complex inputs to the D flip-flop. So an important thing to note is this table here that indicates the D flip-flop's excitation levels. And what I mean by this is it just describes how a D flip-flop works, and that's what we're going to be using in our circuit. So it's essentially saying that if the current value held in the D flip-flop is 0, well, to make it 0 after one clock cycle, we pass in a 0 into the data line. Correspondingly, if we want it to go from 0 to 1, we have to pass in a 1 to the data line, etc. And this is going to tell us how we need to design our circuit, right? Because in our inputs here, Q2, Q1, Q0, they go into a D flip-flop. Luckily, the D flip-flop is super simple. We need to make sure that the values going into this D flip-flop will accurately output what we expect here, right? Because that's what's important. Now, if you use a different type of flip-flop, like a JK flip-flop or perhaps a toggle flip-flop, this behavior might be different. But you can generate what the inputs need to be for each of the flip-flops by looking at this excitation table, and I'll explain how to do that. So for this first input here, since Q2 is 0 and Q2 plus is don't care, well, again, based on what we were describing before, this transition doesn't even exist in our table. We don't have any need to pass this transition into D flip-flop because it'll never happen, right? So we just don't care about it. So we can even say that for the rest of these 3 as well. What about this row? So if we have 0 for Q2 and 0 later, well, what do we need to pass into the D flip-flop? We need to pass in a 0. So that's going to fill it in there. For the second case, Q1 and Q1 plus, it goes from 0 to 1, so what do we need to pass in? Well, we look at this case where it goes from 0 to 1, we pass in a 1 to our D flip-flop. So that would be 1. And then from Q0 here to Q0 plus, it goes from 1 to 1, so what do we pass in? A 1. And what you'll notice is it's almost identical, to what these things are going to be. And you'll see if you map them out like this, they'll be exactly the same. So what we'll do is we'll just fill in the rest of them. But again, this step here is important because if you have different types of flip-flops, such as the JK flip-flop that you want to design with, it might not be the same, right? You have a different excitation table and you'll have more inputs. You'll have like JK2, or I guess you'll have J2, K2, J1, K1, J0, K0. And you'll have all those other inputs. You'll have like 6 different inputs for just 3 flip-flops, and you'll have to design accordingly. But it's the same process. So now that I have the inputs that need to go into my D flip-flops, well, I have everything I need, right? Because now that I have my inputs to the circuit, which are Q2, Q1, and Q0, right? You see them here. And our outputs, which are those inputs to the D flip-flops, well, I can generate this logic equation, right? Or the logic equations to give me those 3 outputs. So what you can do now is you can create one K-map per output that you've got. And so what does that look like? So let's do the first output. I'll do Q2 plus. Okay, that's the equivalent of, D2. Maybe I'll move it over here. Okay, and let's just draw out the truth table, or the K-map like this. So I'll say Q2, Q1, Q0, and then so we'll just label it 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And then we'll fill out the truth table just based on, we'll fill out the K-map based on the truth table. So for K2, or Q2, we have X, 0, 1, X. And then we have 1, 1, 0, X. And so now we can generate an equation for Q2 plus slash D2 plus. Again, I'm writing them the same way because they end up being exactly the same. Like those two sections here are exactly the same. And we can solve by grouping the ones together. So I can group those two ones together. That gives me Q2, Q1 not. And then we can group this one here with this don't care. So remember, don't care values you can group with either ones or zeros. In this case, this is perfect for us because now it gives us a pretty simple term of Q2 and then Q2 not Q1. So doing our sum of products, we just add those together and we get an equation Q2 plus equals Q2 Q1 not plus Q2 not Q1. Alright, I'll go ahead and do the other equations. So to group these ones, I can just group these two. It gives me a term of Q1 not Q0. And that's actually just our entire equation. So Q1 plus is just equal to that. Very, very simple. So now let's do our groupings. We can group these four together. Remember, there's a don't care here. And we can group these two together. And now we've covered all the ones. So this term here is Q1 not Q0. And then this term here is, I think it's just Q2, yeah. Which is really perfect. And then we get an equation Q0 plus is equal to Q2 plus Q1 not Q0. Okay, great. So now we have three equations. We've got this one, we've got this one, and we've got this one. So those are our three equations for our circuit that we're going to build in this little area here. And so I'm going to pull up the circuit now that I've built already that covers this exact same thing that I just designed. So if we look at our equations for Q2, if we look here, N2 has an equation of Q2, Q1 not, right here, and then Q2 not, Q1, and then you OR them together because that's what it says in our equation, if you remember. So, and then so it goes straight into the input of the D flip-flop because again, those are the same inputs. Q2 goes into the D flip-flop since we were able to solve for both D and because they're the same table. I just implemented the Q1, which was just Q1 not Q0, which is easy. It's just an AND gate, and then it goes straight into the D flip-flop. Last one, it's Q2, so it's just this one wire here, and then here we have Q1 not Q0 feeding in straight to the D flip-flop. Now right now it's not doing anything because there's no there's no clock on right now, but we can see that the current state here is 1. I've just made it a little easier to visualize. And again, if you don't see that these inputs are the same, I'm taking in the input from current state and using it in all this logic here. So there's actually no inputs to this circuit except for the clock signal. And I can start the clock signal by clicking Control K. So what you'll see is it'll follow in the order once I turn it on. Again, you don't need to worry about this. This is just me putting a reset so it doesn't lag my computer. But when I start it, it'll go from in this order. So 3 to 4, 4 to 5, 5 to 7, and then 7 to 1. So whatever's here is what the value being outputted is, and you can see that on the LEDs. This stuff here is just kind of a debug thing. I'm just taking in the values from the next state and outputting it so you can see it, but in reality, our counter, let's say it was on your microwave or wherever, this is what you'd be seeing outputted to the thing. If you wanted to design another circuit that has another counter that does something similar, you can use this logic to figure out how to get the order that you want. And if you want to express more combinations of numbers, like let's say you wanted to go from 0 through 9, you need to use 4 flip-flops at least. Alright, because that way you could fit up to 15 or 16 different states, if you'd like to call it. So each one of these things is a state. And if you look at the this diagram here, you can imagine that each one of these is a different state. Because you're in a current state here, and then the next state, you already know what it's going to be based on the logic, right? So you need more. That's how you're going to go about designing your counter in Lab 3. And again, if you need to design it, instead of using D flip-flops with the JK flip-flops, you'll just use that excitation table of the JK flip-flop, which you can search up online, and then map what you expect it to be, Q pluses, into what the input into the JK flip-flop would be to get that same behavior. So that's about it.